Okay, welcome. This session will deal with the issue of landslides on roads, and we will show you a practical example of how we can investigate the occurrence of such landslides using a simplified but efficient way. And this session is divided into two parts. So first I will give you a brief introduction into the study, and afterwards we will have this hands-on workshop in which we will reiterate the coding that was required for doing this study, and this will be led by my colleague Wolfgang Schwanghart, and I will be roaming around here the room to help you if you get stuck. Okay, so as you probably all know, roads are at the core of the transport infrastructure and are key to the economic development of India. They are vital for all kinds of trade, for tourism, but they are also strategically important in border areas. And since the last 10 to 15 years, there has been a huge effort to expand and improve the road network, particularly also in the Himalayan states. And this is all reflected in the news items I put up here. So for instance, Indian growth story accelerated by highway expansion, or India's road network is now second largest in the world. And extensive road network in the Himalayan region will help boosting the tourism sector. But there are also critical voices that warn that the expansion of the road network into the Himalayan region creates maintenance and safety issues. And this is mostly due to because in these fragile environments, there are various degrading factors that affect the roads. And of these factors, mass movements particularly inflict severe structural damage to these roads and degrade their serviceability. And this leads to traffic disruption and impedes the accessibility and compromises rescue operations during extreme events. So having this infrastructure requires a huge effort in maintenance, and so the knowledge about the spatial and temporal occurrence of such landslides is not only important for the early warning, but also for efficiently allocating resources to maintain these roads, and also for establishing remedial measures, for instance, slope enforcements. Now, last year we traveled from Rishikesh to Yoshimat, and on our way we recognized numerous partially road-blocking landslides along the road, and we decided to record these landslides with a handheld GPS. So each landslide is represented by a point along this line. And before we traveled there, the week before, there was a strong positive rainfall anomaly in the entire Indian north. And we mapped the landslides with runouts that affect the road. So landslides that cross the marginal markings of the roads if there was a paved road, and so partially or fully blocking it. And here you can see the measured rainfall from the India Meteorological Department. And these are all the districts in Uttarakhand. And in this week, we did our field survey, and the week before you can see a clear positive anomaly. So Uttarakhand as a whole experienced around 1000% positive rainfall anomaly. So we checked each landslide using Google Earth, the present day and historical images, and classified each location as a new landslide, landslide that was existing before this rainfall anomaly and reactivated landslides. Unfortunately, as of April this year, all historical image from Google Earth from India is not available anymore. And here you can see the results. So this is the road from Rishikesh to Yoshimat, and this is overlain on a map of the litho zones. I will cover this later. And all the dots represent the landslide, and the violet color corresponds to the new landslides, the yellow color to reactivated ones, and the greenish bluish color represents the previously road blocking landslides. And you can see that there seems to be a clustering along the road. And then we checked which geo-environmental variables could explain the occurrence of landslides. And we came up with first slope, because the road crosses steep terrain with soil mantled slopes that range in inclination from 20 to 40 degrees. Next, we presume that rainfall patterns exert a strong influence on the occurrence of landslides. And this is a map showing here the climatology from WorldClim 2. But we need a more specific picture of what happened during this short time interval when we were traveling. And for this, we choose 5 rainfall products to assess the spatial patterns of accumulated rainfall from January to October 2022. And these are all they're different rainfall products, either based on rain gauges only, or rain gauges and satellite observations, or rain gauges, satellite observations, and reanalysis data. And we choose the CHIRPS version 2 because this has been shown to have a good performance in similar regions. Now, most of the study area lies in the Lesser Himalaya, between the main boundary thrust in the south and the main central thrust in the north. And we simplified the geology by reclassifying the lithological units in so-called lithozones. And the Lesser Himalayan sequence is mainly composed of sedimentary and low-grade metasedimentary rocks. And the most important lithozones are lithozone 2, 4, and 5. And these correspond to phyllites and quartzite, shale, quartzite and igneous rocks, and high-grade metamorphics. And since we are here in a tectonically active region, we have a lot of faults and inhomogeneities in the rock, which serve as important seepage pathways. And in regions where these rocks are sheared and fractured, the hill slopes may be particularly fragile. So we have our 3 main variables that potentially affect landslide occurrence. And of course, the construction of the road itself could be a major cause for landslides, because the improvement of the road network involved the widening of the roads, thereby undercutting the slopes and destabilizing the hill slopes. So we included also road widening, and we searched for data on the road widening along this highway, but we only could find data prior to the monsoon season of 2010. And this is shown here with these white stippled lines. So these sections of the road have been widened. Now we conceptualize the landslides along the road as a network attached point process using the PPS extension of Topotoolbox, a spatial point process is a stochastic mechanism which controls the spatial distribution of events. So Wolfgang will give you an introduction to this later. And yeah, we model the landslide densities with an inhomogeneous Poisson process where the events are all independent from each other. And apart from slope, precipitation, lithology, and road widening, we also tested the effect of land cover, the curvature, the roughness, and the distance to faults. And this is here shown the profile along the road in the upper panel with all the black dots indicating the landslides. And the second panel, panel B, shows the landslide density. And the third panel here shows the accumulated rainfall all along the road. In this slide, the second panel shows the mean upslope gradient. So the gradient was projected onto the road. And the last panel shows the litho zones along the road. And you can see it mainly traverses litho zone 2 and 4. And in this slide, you can see the region where road widening has taken place. And in the lower panel, you can see the modeled landslide density. And if we compare with the measured landslide density, we get a quite similar pattern with a high landslide density in the beginning, in the first 75 kilometers or so, and then declining to a low landslide density. And at the end of the road, there's another slight increase of the landslide density, and this is pretty well covered within the model. Now, I said we also checked for other potential variables that could affect the landslide occurrence, and this is shown here. So we have here the IIT information criterion and the adjusted R squared, and we can see that the rainfall, the gradient, litho zones, and road widening have the strongest effect from all the variables. And when we add more of these variables like land cover, total curvature, roughness, and the distance to faults, we don't see any big improvement. So to conclude, the main controlling variables for landslide occurrence along this highway are the slope angle, rainfall amount, the road widening, and lithology. When we correct for all these other variables, road widening leads to a doubling of the road blocking landslides. So we cannot change anything regarding slope angle, rainfall amount, or lithology, but we can try to somehow work on the ways we construct the road. So improper construction practices of road widening increase rather than decrease landslide hazard along roads. And this demands for proper geological assessment and mitigation measures, such as constructing retaining walls, installing drainage systems, and stabilizing slopes to minimize the impact of road widening on landslide occurrence. Yes, and with this image, I'd like to thank you.
Thanks, Jürgen, for giving let's say, the introduction to that topic that we will be working on today. So before we start, who has actually worked with Topotoolbox before? Can those please raise the hands? Okay, back there, great. There, okay. For those who haven't, have you worked with MATLAB? Who's working with MATLAB? I know that probably many people are nowadays working with R or Python for these tasks. Topotoolbox is still written in MATLAB. Nowadays, I feel like I have to apologize for that. But let's see what the future brings. So far, this will be all in MATLAB. For those who have no experience in MATLAB, but you do any other programming, don't be discouraged. You will understand the code, I guess, more or less. If you do Python, there are a lot of similarities between both languages. And so I guess you will grasp the point anyway. So what I'm not going to do today is actually a very basic introduction into Topotoolbox. Actually, I wanted to cover something which is more advanced, and looking at, well, the way how we approached the study that Jürgen just presented, okay? And so this approach is actually about point patterns. And point pattern analysis is something that you do in spatial statistics. So the other question, did anyone do something on or some work on spatial statistics? Please raise your hands. Okay, there's one. So you're more engineers, it seems to me. Like, not some, or any, but you have statistics a lot here, I guess, also in your work. Okay, so what is it all about? Well, what I want to do is to show you how we approach this problem using Topotoolbox. Just shortly, Topotoolbox is a software for the analysis of DEMs, or digital elevation models, in MATLAB language. And, well, the main purpose of this software is to provide a library of functions to compute, for example, flows of sediments and water across landscapes, simulate landscape evolution over long geological timescales, to infer rates of geomorphic processes from DEMs and geochronological data. And it also has a lot of capabilities to visualize all the analysis results. So Topotoolbox was, well, was mainly developed by me and together with Dirk Scherler, but also others. And it's, for a software, it's already quite old. So when I started coding, that was now more than 15 years ago. And with that, I also developed Topotoolbox. And it has remained a software that I've been constantly working on and further developing since. So it's still used a lot. And I hope that by attending this workshop here, I can convince you in some way that it might also be useful to you. So in the end, Topotoolbox has a lot of capabilities that intersect with GIS capabilities, okay? So a lot of stuff that we do in that software you might know from QGIS or ArcGIS. But here we use a slightly different approach using, let's say, objects, numerical objects that might be more naturally to work with as a hydrologist or a geomorphologist. So what are these objects? So Topotoolbox relies on a couple of numeric objects. And the three most important, first of all, are, let's say, the grid object, the flow object, and what is called a stream object. The grid object, well, that's basically a DEM, a digital elevation model in a raster form. You usually get these from publicly available sources as a TIFF, for example, or as a ASCII file or a TXT file. Then, based on this DEM, one of the major things that basically is the numeric core of Topotoolbox is the derivation of a flow object. This is basically the flow network. So Topotoolbox relies a lot on graph theory and network analysis to make this step particularly efficient and to do these computations efficient. So a flow object, so sorry for being very theoretical here right now, I'll show it in a second. But this flow object stores flow directions derived from the DEM. It can do single or multiple flow directions. And due to a topological sorting, the speed at which we can do these calculations are hundreds times faster than in any GIS. And then finally, there's the stream object. Well, that's basically a reduced form of the flow object. So, or you can call it in network theory or in graph theory, a subgraph. So it's a part of the flow network which we could consider as that part of the landscape which is where you have permanent flow. So rivers, streams, not the hill slopes. Also here, we make use of the network structure. So the general idea is basically a very linear one at first. Well, as I explained before, well, you start with a grid object, you derive a flow object, and then you can create a stream object, which gives you the flow networks of a landscape. Okay, that might sound very easy, of course, it is also, and very linear, but in fact, it all comes together if you then apply these tools that Topotoolbox offers, so that, for example, once you have delineated streams, well, you can also create grid objects again, and so you have a lot of interaction of these objects, and based on these, you can work out workflows and all kinds of batch analysis. And well, I will show a couple of these just right now. And in fact, stream object, grid object, flow object, those are not the only objects that Topotoolbox comes with. We have enhanced the software with a lot of other objects also. So one example is, for example, a swath object. Well, that's just a numeric way or object to do swath profiles. Then Dirk Scherler recently developed a divide object. So you see that we as developers are basically also, we are mainly geomorphologists, so thinking about landscape elements. And so divides are an important part of the landscape. So we have that divide object, and I think we are the first ones to ever do this. And then finally, there's PPS. And that's what I'm going to talk about today. This is the point pattern on stream networks object, PPS. And it's actually very simple because it is just a combination of a stream object with points. So what that is going to mean, I will show you in a second. So in order to get started with Topotoolbox, it is necessary to have MATLAB. This is proprietary software, so I hope that IIT has a license, but from what I know, they do. And you also need a couple of toolboxes, of which actually two are mandatory, or actually only one. Actually, only image processing toolbox is absolutely mandatory. Mapping toolbox is definitely good to have. To import and export geographic data. Statistics and machine learning toolbox is something that we need today because it offers the tools for all kinds of statistical analysis. And optimization toolbox, parallel computing toolbox is good to have, in particular the last one, if you want to speed up some of the computations, if you run them in parallel. So then download the latest version of Topotoolbox. As I said before, you will find those also on the Topotoolbox blog. It's on Git, or this link here also leads you to Git, a versioning system where Topotoolbox is maintained. And once you have done that, you need to tell MATLAB where Topotoolbox is. And so MATLAB does that with a so-called search path. So it just needs to know where the files are or the functions are that it can use. And so there is a possibility to use @path or so, and you will find also a description in the README file in order to how that can be done very efficiently. I can also show it just in a second. Okay, so that I'm going to show. again, Topotoolbox mainly relies on these numeric objects. And for each numeric object, there are a lot of functions. So for example, if you have the command window and type methods grid object, it will tell you what kind of functions there are to work with grid objects. And for example, for grid object, there are a couple of things that you probably know, like creating contours, for example, to calculate the slope. That one is not even complete, but for example, gradient 8 is a way to calculate slope. For example, to fill missing values, inpaint NRNs. It's uses a method called inpainting. And so a lot of different techniques and functions to work with a grid object. Okay, so those working with, let's say, Python or R will probably often work in a very similar environment in terms of how the GUI looks like, or the IDE, the Integrated Development Environment. Just for those who have not worked with MATLAB before, just a very brief introduction. Well, here on the left-hand side, you see the folders. This is where we will work now, and this is also the folder that you can download using the link that I sent you. The data, or this folder contains the data, as well as an analysis script, which is slightly simplified compared to the one that we used in our study. And yeah, we will get back to that. But before we do that, just to briefly show you the first initial steps. Okay, so you have installed Topotoolbox, or you have installed MATLAB, you have installed Topotoolbox, you added Topotoolbox to the MATLAB environment using add path. Then you can just run an easy example. So Topotoolbox comes also with a DEM at the beginning. And so you can tell MATLAB, okay, I want a new variable called DEM, and that one is a grid object. So in that case, grid object is both the name of the object as well as the so-called constructor function. So I'm creating a grid object using the function or the constructor function grid object, and SRTM. So this is the file that comes with Topotoolbox. It's the SRTM of the Big Tahunga catchment in California. It has a 30-meter resolution, so nothing particular special. Okay, so once you did that and you run that command, it will return a new variable in your workspace, which is called DM. Well, that's what we defined. And that value is a grid object. Now let's take a look at what is actually in this object. Okay, why do we actually use objects? Well, if you think about what a grid is, it's basically very simple. It's a matrix of values, okay, in that case of elevation values. And, well, there's just a little bit more that we need to make it a geographic grid. I mean, it needs spatial referencing. So we need to know, for example, where is the left lower corner actually located in a coordinate system that translates somehow to a location on Earth, and what is, for example, the cell size. And since there are a lot of different projection systems, at best you also store what kind of projection you are using. And that is actually in here, okay? Once we open or double-click DEM, we can see, okay, there's a matrix with set or matrix set, which contains all the elevation values. It's not particularly large here, 643 rows and 1,000 something columns. It has a cell size of 30 meters. There's a referencing matrix, which is basically used for referencing the grid somewhere on Earth. The size again, the name. There are some possibilities to store X and Y units and Z units. And then there's also georef, and if we double click on that one, we can also see, okay, there's some information. And so here you will see that this grid is stored in a UTM, so Universal Transverse Mercator projection, in zone number 11, so that's somewhere in the US. So here, which zone are we located in here? 44, exactly. Yeah. So there are a lot of functions to visualize this DEM. So of course, what you can do, for example, is use the command image sc. That means it's a scaled image. It's actually a MATLAB function or a core function. But what you can do with objects is that you so-called overload these functions and apply them to your object. In that case, I used it, and I used image sc because it's the common function to plot scaled images. So if I do that, you will see the DEM just as a color image. That is nice, but it doesn't really, it makes nevertheless reading the landscape a bit difficult. So it's often better just to plot the image as a hillshade. And here the function is image schs. So I need to apologize that function names are sometimes a bit clumsy, but well, what shall I do? That's how I did define them at the beginning, and all the documentation works with these, so it would be a hell of a work to change that. So image sc, scaled image with a hillshade, hs, then produces a hillshade of the DEM as shown here. You can, of course, also create a 3D image of it. For example, if you use the command surf, it shows it's a surface. And then you get such a surface. And actually, MATLAB has quite some nice visualization capabilities. So you can say, okay, I want some lighting also. I want the material to be not so reflective, so a little bit dull. And then suddenly you have a nice looking 3D model that you can explore. So I think that's one of the main strengths of MATLAB, to have this integrated way of visualization and so on without, too much, or that you don't need extra libraries for that. Okay, so for example, also what you can do with the DEM is to calculate gradient. So, or the slope. So for example, the function gradient 8, or let's take another one. They're slightly different in arc slope. We'll calculate the gradient. So just this, the semicolon is needed if you finish a line that it will not print the output to the command window. If I leave that away, well, it will return what is basically in G. If I don't, G, so then it will not print the outcome to the command window. So now what we did, we produced a new grid object which contains the slope. Okay, and also here we can plot both together if we like as a surface. Let's use some cam lighting again. We adjust a little bit this axis because there's a lot of uncertainty in the slope, so that we don't have the color map affected by very large values too much. And yeah, let's use a different color map. Magma color like this. Let's see whether it works. And so you quickly get a 3D slope map. I think that's not so nice. Let's make it the other way around. We flip our color map, and here we go, and have a beautiful slope map just within a few seconds. Okay. So if I'm going too fast, or if there's anything you want to know in between, that's why we are here, okay? Just raise your hands, ask, and we hope we can answer every question. So, based on the grid object, based on the DEM, we can then calculate the flow object, as I said before. I usually name this FD for flow directions or so. And we can create a flow object based on the DEM. You will see there are also a lot of different options to do that, but let's just use the very basic one. So just perhaps one note here. If you are doing stuff like this in GIS, you will usually be asked, or better, okay, we need to fill the DEM first. That is not required here. It's doing this internally, but in a more clever way. Because what happens when you flood fill the DEM before calculating flow directions, that means you're discarding all the information within the topographic sinks that you are filling. So don't do that. It's Topotoolbox takes care for that. Okay? So now I derived a flow object. It's called FD. And FD is here also in my workspace. You can see, okay, it's a flow object. And once we double click on here, you can see what's in it. Well, again, it has some size. Tells me it's a single flow direction algorithm. But then there's some weird stuff in it. Okay, there's no grid in it, like you would get in GIS. But it's a list, or two lists, basically, of indices. So what do they mean? Well, they just say that, for example, the cell in EX, let's say the first one, drains to the first cell in the EXC vector. Meaning, okay, we can have a look at it. So the cell with the linear index, so the one with 769276, it's just numbering the cells in the DEM. So this cell here is draining to this one here. Okay? And the second one, this here, is draining to that one. So it gives us flow directions, just links between individual pixels. And the special thing about the way of storing it like this is that we also store these lists here in a topological order. That means this one here, probably the highest or this one doesn't receive anything from any other neighbor. It doesn't have any contributing pixels. And so we can go through that list which ensures that we don't miss any of the upstream pixels. And the good thing about this is that means that most of the algorithms work in big O n. So meaning in big O notation, most of the algorithms that we have are just a function of n and not n squared or something like this. So that means they work for pretty large DEMs in a very efficient way. And so, for example, when we calculate flow accumulation means the amount of water, the amount of area draining through each pixel. We can do that pretty quickly. So when I say, okay, I want to calculate the flow accumulation based on our flow object. So flow-acc means flow accumulation. It needs FD. Then it's just in a matter of a second, or less than a second, that we then can calculate A. We use a slightly different color map here. Let's use flow color. Okay, that can't be seen very well, but you can see that by doing that, we can calculate the river, basically, and the location of the river and how much water, or let's say how big the drainage area for each pixel is. Okay, so if you do that for the entire Himalaya, let's say with a SRTM3, so with a 90 meters spatial resolution, Topotoolbox can do that in about 6-7 seconds. And in GIS, it takes an hour or so to calculate. Okay. Now, with flow object, you can do, of course, a lot of different things also. Again, if you type methods flow object, it will give you all the functions that are available. Some of them have a bit of cryptic names, others are perhaps not so. unclear what they do. For example, drainage basins. So if you want to derive drainage basins, we can do this. Just see, and we get a delineation of the drainage basins. Okay. Now, I said before that based on the flow object, we can create a stream object. Okay, a stream object is just a subset of the flow network. It's also just stored as a network, but it's just smaller. And in order to define a stream network, the only thing what we need is a way to say, okay, where do streams actually begin? Okay, of course, that's often not so easy to answer. Because this might differ a bit from place to place, depending on climate, of course. It might depend on, let's say, the subsurface properties. So something which you have to decide upon in when you use this. But let's say what often helps is just to use a minimum upstream area. So you say if there are more than 1,000 pixels, for example, flowing together, that's the point where there's enough area basically to have permanent flow. So that is what actually is also required if you use a stream object, or if you call it, or if you construct a stream object. It takes our flow object, and then we can say, okay, we want a minimum upstream area, and that one here, the unit is in pixels. So if we have 1,000 pixels flowing together, then we have a stream object. Again, when we just take a look at what is in that object, again, some information about the size, the DEM. Again, we have these vectors here, EX and EXE. They are more or less the same like the ones that we have in the flow object, but just smaller. And then there are some additional vectors. Most of them have the same length. X, Y, well, that's the X and Y coordinates of the stream network. And these here, X and Y, perhaps we will use that term here also. They are node attribute lists. So it means for each channel location, there is a value, and these are stored in so-called node attribute lists. Okay, so for example, now that we have that, again with a stream object, we can use, for example, plot. And so here we have the stream network. For those who haven't used MATLAB before, but that's very similar to other languages, you can say, okay, I want the color can be red, for example. Then you have a red network, for example, a line, line width. You can change the width of or thickness of the lines. All that works as in the common plot command. So, but that's basically it. For example, just to give you a brief example also, now we have a couple of drainage basins here. Some of these rivers flow northward, others here. Let's say I just want to have the biggest basin and work with that one. Then there's, for example, and that's a very clumsy name, K largest concoms. That's because, well, it relies a lot on graph theory. Is I want to have the K, number K, some integer value, largest connected components. So one drainage basin is basically a connected component. So and if I just want to have the biggest one, I can do it like this. And then if I plot it again, then I only have the largest network. Okay? We can also plot, for example, river profiles like this. This is the river profile with distance upstream. Here it's about 50 kilometers and the elevation on the y-axis. Okay, so that's just very briefly on some of the workflow that I showed before. So you have the grid object, flow object, stream object, and some of the capabilities that Topotoolbox has. Now I told you that we want to work on point patterns. Okay? So what actually is a point pattern? Okay? What is a spatial point pattern? Well, A spatial point pattern is a data set providing the observed spatial locations of things or events, such as, now there are some examples, trees in the forest, mapped gold deposits, earthquake epicenters. So things that you can conceptualize as points. Of course, you can also conceptualize aerial features as points at an appropriate spatial scale. Now, the important notion behind that is that the locations are what we call a realization of a stochastic process, or stochastic spatial point process. So, what we see when we, for example, look at the distribution of trees along a forest ecotone is one potential realization of a mechanism that we wish to understand. That's often the case. If we have earthquake epicenters, well, that's also to us a not purely deterministic process. There's a lot of stochasticity involved. And what we see is just one possible realization. And from that realization, we want to infer what basically controls the spatial distribution of these earthquakes, for example, or trees. Okay? So the aim of point pattern analysis is to describe the processes or mechanisms that generate the density of points. So now I was saying, okay, this is a classical way of point pattern analysis, which you learn in spatial statistics. Now I want to do that today with you with point process on a network. So, and why that? Well, because many phenomena in geomorphology, but also in hydrology, occur along or on river networks. Think of riverbank failures, of landslides just happening because the river undercuts slopes. Landslide dams, nick points, log jams, beaver dams. So a lot of different phenomena that are just not freely moving or freely occurring in space, but they are attached to a network. That's actually the same if you think of road accidents. If you want to model them, you cannot just look at a map of, or at Delhi, for example, but you need the road network of Delhi because, well, obviously accidents are attached to the road network. Okay, so Topotoolbox has these capabilities with its new object PPS. So PPS, that's where we were. And what we want to do with it, is to understand what we think are, let's say, the main controls on why points are located in a way how they are. And we can classify these two processes or controls into two different types. So the first one is, let's say, a first order process. And that one is that produces a variation in point density in response to some causal variable. Okay? So think of the distribution of trees in a forest consisting of different types. Then, for example, water availability will play a role. The type of soil will play a role. Exposure, or nutrient availability. This will control to some extent whether we have trees at a specific location or not, or it will somehow affect the density of trees. But there's also another process involved. And that one is what is called a second order process, which results from interactions. Meaning that if you have a tree somewhere, it's often very likely that you have another tree nearby. Okay? Due to germination and the distribution of trees, that will happen. And that will cause something that is called autocorrelation. Okay, so, and in the end, we can think of a point process as somehow being generated by these two different mechanisms. We have first order controls, and we have potential second order process controls, which somehow mean how do I mean, could points cluster, for example, because of germination, for example, but also might there be inhibition simply because of the fight for nutrients, or let's say because a plant is making shadow so that it's difficult for another plant to grow nearby. So we will mainly look here at first order effects, because now we are coming to the point where we are talking about landslides, okay? We can think of landslides when we zoom out far enough, or if we talk about very small landslides perhaps, as individual points that, and now in our case what we did, are happening along the road. Okay, so they are point features which are attached to the road network. And yeah, the question here is whether such second order processes might play a role. What do you think? Can you think of any way what a second order process in landslide analysis could be? Any idea? Actually, I find it hard to find one. I mean, you could think of, okay, that one landslide produces enough impact, so and ground shaking, and by that it might trigger another one. Okay, perhaps also it might cause one landslide might change the way how water moves through the landslide through the landscape and will affect the adjacent areas, and they will also react with landslide. That's the kind of interaction that I'm thinking of, but it's probably not the case. Okay, so mostly we will look at first order controls, and we think of those as perhaps slope, land use, lithology, whatsoever. Okay, and these are the ones that we want to explore. Okay, we will do that with PPS. And before, I mean, we're taking a lot of time here, but I hope that's okay. Before we do that, let me briefly show you what a PPS object is. Now, I said before, it's actually pretty simple. What it requires is a stream network S, and then we can supply some locations. So here, this is an option. PP means for planar point pattern, or point pattern, which we could provide as X and Y coordinates. And then optionally, I can also add a DEM to that object. So in that case, you would have a network, stream network, points, and some annotations, and all they together give a PPS object. Another way to create a PPS object is using simulation. So for example, if we think, okay, we have a completely random distribution of points along the network, we can use, for example, a point density. So for example, so and so many points per meter, and define our an instance of a point pattern doing this. So let's just do this with the point, or with the stream network that we just had. So let's call it P equals PPS. We have a stream network, and then we say, okay, it has a random Poisson distribution with a density of 0.001 or so. Oh, that's perhaps so and so many points per meter. Okay, so you call that also the intensity of the point process. And again, we can supply also the DEM. That's not strictly necessary, but it makes things easier. Okay, let's plot P. Okay, that's one potential realization. It's just a stream network with points on it. Okay, just completely random. We can run that code again, and it will look different, okay? And we can, let's say, increase a little bit the density. Then we have a few more points, okay? All these are, let's say, completely spatial pattern, a completely random spatially pattern. CSR, complete spatial randomness. So before you do any analysis on these, if you, let's say you have a distribution of landslides along the river network, then perhaps one of the first things you would want to ask is, are these completely spatial random? Because if they are, it would be probably a bit disappointing, because if something is completely random, well, then it perhaps doesn't make too much sense to continue working on it. You would wish that there are actually some deterministic controls so that the point pattern deviates from a purely random pattern. But for example, in order to test whether this pattern here is purely random, there's one test, for example, CDF test. And, well, it returns a 0, meaning that actually, in that case, we cannot reject the null hypothesis that this is random. Of course, well, we created it in a way that it's random, so this is what I would expect also, okay? If we do that again, it's 0. And why? Well, here we are testing on a significance level of 95%. So we can expect, I mean, that it happened so early, okay, but that's luck, is that about 5% of the randomly generated point patterns are actually recognized as having structure in them, as being non-random. Well, but that's the case with hypothesis testing. Okay? So that's probably a good way to start. If you have your point pattern, is it random or not? If there are only a few points, it will be difficult to show that they actually deviate from a random behavior. So the more points you have, the better. Okay, we can also create a point pattern, which is, and now let's see, we'll come to that point later on, which might look like this one here. Again, is it completely random? Well, perhaps not, because it seems like, if you remember that catchment, here's the outlet, we go up in that direction, and it seems like the density of points is increasing in this direction. Okay, so when we call CDF test on that newly created point pattern, it tells us, we can simulate one again. It's not random, okay? There is some control in it. And well, in that case, I simulated it in a way that the intensity is a function of elevation. And so when we plot our point pattern in a long profile, you can see that the further we go up, the more landslides or points we have. Okay, so if we think there are potential controls, like in that case, I mean, we have simulated it, that there is a dependency of the point intensity on the elevation. Now, how can we explore that? I mean, now we know that there is, because, well, we told Topotoolbox to distribute the points this way, but usually we get points, and we try to infer the mechanisms. And I would say there are two main classes of ways of doing so. One is, first of all, with exploratory analysis, and the other one is using parametric modeling. Let's look at the exploratory analysis first. And one of the functions that might be very helpful in that case is the function ρ. Here we look at whether there is a dependence from some covariate in a non-parametric way. What does that mean, in a non-parametric way? Well, we try to fit actually a model which shape we do not define a priori. We just say, okay, we do some smoothing. And so we only have to define a bandwidth parameter or something like this, which will adjust the curve that we see. But otherwise, the curve is free to do whatever it wants. Okay? Let's try this here. When we use ρ, and now let's see, I'm going to start the parallel pool. Let's see whether I get an error again. It seems like the parallel pool doesn't cope well with when the computer goes into standby. So that's something, what we now fitted to our data, or not really fitted, how we explored our data. On the x-axis, we have actually the elevation. And on the y-axis, we have the point density. And that tells us, well, we have relatively low intensities for low elevation, and then they seem to increase. So that's one tool how to look at, let's say, bivariate relationships, and which helps us to explore, are there dependencies on particular variables or not. The other thing we can do is parametric modeling, and that requires us to define, well, the shape of the model. In that case, we are only using a function called fit log linear. We are fitting so-called log linear models, which basically look like this one here. Okay, so they can also be bivariate and they can be more complicated. Here we just use simple linear models in a log space to fit such a what is called inhomogeneous point process. And when we do this, and we want to fit it to the DEM, okay, so when we want to see, well, what's now the effect of DEM, that's then shown here. So that is a more parametric model of how point density, let's say landslide density along the river network, are dependent on the variable set or on elevation. Okay, now we have simulated everything, like from, we know that this model exists like this, since we have simulated our model that way. Doing it here, simulate the intensity is a function of the DEM divided by 1,000,000, so that's just to make a reasonable density. Okay, I'm sorry that this took quite a while, just to give you the background on how we approach that way, how we model then points or landslides along the NH7. Let's say introduction on point processes and the way they are implemented in Topotoolbox gives you an idea how that works and how you can perhaps also do it yourself then in the future or after that course. So the script has some explanations in it, of course, but not like line by line. I will also not talk about each line in detail. It's something that I would also ask you then to explore in more detail. This is in particular the case when we talk about plotting. Okay, those amongst you who write their own code and own software will often realize that code required to do plots is often the longest code, simply because there's so many options and stuff you can make. So these sections become really long, and I don't want to talk too much about them here. Okay, so it's more about these ways how to fit data and how to explore them, and then I hope also that we can together discuss the results. Okay, so so starting from here, so we have a DEM, and we have a lot of different data that we will use as potential predictor variables. And Jürgen already talked about it, that we used a couple of different variables like road widening, like precipitation, like slope, lithology, which, well, we first of all need to import and to then digest so that it's working with Topotoolbox. So in that case, we are having a DEM. I think it's the COP30 DEM. It's the latest, and to my impression so far, best globally available DEM. We have that for the region, and you also have that. It's located here in the DEM folder. So that's why I'm calling it DEM /DEM to load that data. Then we have data on the roads. We can read these are shapefiles using shaperead. We have the mapped landslide locations also as shapefiles. Again, we can read these with shaperead. So this is a function that comes with a mapping toolbox. Here you need the mapping toolbox. And well, I'll just take this first part of the code, so this code section, and there is a button to just run that section. Let's do that again, because at the end, it will show us the data, the DEM, as well as the road network and the landslides. Okay, so that's kind of the figure that Jürgen also showed previously, showing the landscape, showing in black the road, and in red the landslide locations. So then, let's say what is not so obvious is the next step is to derive the road as a stream network. Okay, so that's a bit weird. Why would we represent the road as a stream network? Well, because that's basically how Topotoolbox works. That it's if you have a network, then it's called a stream object, right? But a road could also be such a network. Let's say the difference is, or what is the difference between a road network and a stream network? It does not follow elevation exactly. It's not necessarily dendritic. Okay, a road network can be non-dendritic, and that's the case. Since we are only looking at a single road here, well, what we are looking at is a very simple network. You might apply that that technique, nevertheless, also to more complicated networks or more complicated road networks. Now think of these as, if you have a road and then you have something like this, then this is not a dendritic network. So it's not even necessarily directed. Okay, a stream network is also a directed network. This is an undirected network, so you can go in both directions. But nevertheless, you could represent this as a directed network using what is called a shortest path net, or the shortest path graph, that you create a network that goes like this, and perhaps from here to there, and from here to there. Okay, so I'm just showing the ends of these networks. Like here, you would go then like this. This would then be a directed R-cyclic and a dendritic network, but you're not getting these connections here correctly, okay? That would be the only drawback. There are also other software packages that do this, okay? Topotoolbox is not the only one that can do point pattern analysis on networks. So if you're working in R, you can use the package spatstat. And perhaps there's something similar in Python. Since I'm working in MATLAB and using Topotoolbox a lot, I decided for that problem, okay, I'm using my own tools. And in that case, it was straightforward to say, okay, I can represent a road as a directed network. Okay, it's a bit tricky to do that. I'm not going to explain that in detail. But the code, you will find it here. To extract the road network and to say, okay, that should be a stream. Let's just run that. Okay, what it returns is P, what we got to know. Let's plot P. That's basically the road. Well, it's attached basically to the pixels of a DEM. So it runs along the pixel centers of a DEM, and it has these points on them, which are the landslides. Okay, so first thing we could ask here is this, and that's not in the script that I gave you so far, but you have already learned that one. Is it completely random? Okay, CDF test, and we have to reject the null hypothesis that these landslides are randomly distributed along the network. Well, that makes intuitively sense if you look at the distribution, that there are parts where you have a high concentration of landslides and other parts where low concentrations. Now the question then begins, well, what causes these discrepancies? What causes these patterns? And that's what we are going to do. Okay, we can perhaps only just for fun, we can also say, how would a random network look like? We can also just, in that case, you can use that tool, just random p. Now this would be a random pattern with the same intensity, so the same density of landslides as the ones that we measured them. This would be completely random. Okay, road widening, okay, that comes as a file that Jürgen prepared. It's more or less a polygon file. In that case, we can convert this to a grid object, and by that, we can also then use it as a predictor variable. I'm going to do that here. So if we look at what that predictor variable looks like, probably more like, okay, like a big road. So the road is basically running through these areas from which we know where that road widening took place here. So then rainfall data. That's something where Ravi here in the audience also worked on, and he contributed that particularly. So we were not entirely sure when these landslides had happened, okay? What we knew is, because we were visiting all the site and we're going there by car, is, well, they must have been still quite new or quite fresh, because many of them were still blocking the road. Okay, the debris had not been removed. We have also seen this year. Many of the older debris was already removed, but apparently during the strong monsoon this year, there were a lot of new ones. And I think that question came before also. There were a lot of renewed ones, so reactivated landslides that had happened along the road. And so one particular important variable to explain the patterns, we thought, of course, that must be the spatial distribution of rainfall. Now, in the Himalayas, unfortunately, the landslide, the rain gauge network is quite sparse. And so it's difficult to get station data, which is representative enough to study that. So we relied on other precipitation products. So for example, CHIRPS, version 2, IMD, so it's Indian Meteorological Department, also 1 and 2, IMERC, and MSWEP. So all different products with partly different spatial resolutions, which would provide us with predictor variables. And so in these few lines of code, what I'm doing is I'm reading that data. I'm also, since they come in WGS coordinates, I'm also projecting them here to our, so that's what this function does. I'm projecting them to the DEM. And yeah, let's just look at that. Oh, well, there's nothing to look at. It's basically just running it, and it takes a few moments to finish. So, but what it returns is an array where all the precipitation data is stored in a way that we can access it or access that data as input to our model. So still a bit waiting. So the data is in total the daily rainfall for 2022. So the total accumulated rainfall until the 10th of October, that's when we did our traveling, in 2022. Okay, so that is done. It's here in str in that variable. It's a structure array. So here are different grid objects for each precipitation product. Now let's visualize that. That is also something that Jürgen has already shown in a slightly different way, I think. But what it shows is that these products differ vastly, okay? In terms of the accumulated rainfall during the entire year. For example, CHIRPS and IMD1, the patterns are completely different, okay? IMD1 and IMD2 are quite similar. IMERC also, but yeah, it just shows how problematic it is to work in that environment with these relatively coarse-grained precipitation products. And you really need to take care which one is the best. But which one is the best? Well, we don't know. There's no validation data, and sometimes validation data would not be appropriate because some of these data sources actually apply these data to train or to interpolate rainfall data. So we will look at that in a second. But before we go on, we also need to load the other covariables. And the covariables that we generated was, first of all, gradient next to the road, meaning the idea was that, okay, the steeper the slope next to the road, the more landslide activity we would expect. Might be a possible hypothesis. Okay, here there are a lot of variables that we set. For example, well, do we need to look at the entire slope, or is it just sufficient to look just at the slope adjacent to the road? Here we decided, without any very good reasoning, I would say, just on to say, okay, it's just the 7 pixels around the slope, about which, so it's about 200 meters, 210 meters in the distance from the road, on which we calculate the slope. You might say, okay, hey, you can also just take the gradient just next to the road, okay, just in 30-meter distance. But then I would argue, okay, slope itself is so susceptible to errors, to uncertainties, that making a bit wider swath around the road makes sense to average out some of this error. So we also just looked at the slope upstream, or upslope to the road, not the one downslope. And so this code here shows you how to do that, because it's not so easy actually just to extract the lower or upper parts. It's not like just buffering. Okay. So what it returns here, the type of variable that we get is GM. So it's just a gradient, a mean gradient, upslope to the road. And when we plot it, how do we do that? Okay, so this is shown here. So this is the road, the elevation profile of the road, and the coloring indicates the steepness next to the road. Okay, the more yellowish the colors, or the greenish, the higher the slope next to the road. There are a few sections where it's apparently quite, so when you go to Srinagar or so, the slopes declined a little bit. And then as soon as you go up into the higher Himalayas, of course, there's high slope. But at the same time, you see that these values also fluctuate a lot. And that's also inherent in calculating the slope, again, that there's a lot of uncertainty. And that might also affect, when we go laterally along the slope, that along the road, that will not change that quickly, actually, in reality, as it does, or as it is suggested by these values. So we might use a little bit of smoothing. Okay, we might smooth along the road these slope values. And this is something where we can actually already start to interact with the model, that we say, okay, let me find the optimal value for that smoothing so that it increases the predictive ability of my model. So for example, we might say, okay, we might want to smooth our gradient along the road using some smoothing factor k. Now this becomes difficult to read, I'm sure. So we are smoothing this. We are fitting then a model to this smoothed value and extract the deviance of that model. That's a kind of measure of the goodness of fit. And do this for all k values. And these k values are just smoothing factors. The smaller they are, the less smoothing. If we choose a very high value, then a lot of smoothing. Okay, when we do this, we get an optimal K value. So that's a smoothing value which optimally smoothes our slope values so that our predictive ability of our model becomes optimal. I would have been very surprised if that would have been a very large value, because otherwise we would get, it would be, then it wouldn't make sense anymore. But in that case, an optimal K value of 4.3, that's quite okay. So if we plot, it's in the same way, you know, it doesn't hardly affect the visual appearance, how the slope has been smoothed. So the color values, they have declined a little bit from 60, the maximum value, to 60. Of course, if you smooth it, you will smooth out the peaks. But otherwise, you know, it's not too much smoothing, it's just a little bit. Okay, now let's look at the individual effect of slope on our point pattern. And again, what we will use here is the function Schwanghart. I've explained that before. That's a non-parametric estimate of the dependence of the point pattern on a particular covariate. So in that case, let's check out how the point pattern actually depends on our slope. Okay, so what we see is that, as we assumed, well, there are hardly any slopes, any landslides where you have low slopes. Okay, and then they tend to increase and to increase in frequency until to some variable, to some value of slope, 40 degrees here, and then it becomes a bit uncertain here. Okay, so we have a drop which doesn't actually make so much sense. And there might be reasons for that, either because the number of occurrences of these slopes are actually very low. And so you see that also by these so-called bootstrapped confidence intervals around these estimates, that they are becoming quite wide. An advantage of the approach that we are taking here is that we can actually change the input slope or the input covariates as we wish, actually. So in that case, the idea was, well, you know, you see that decline here, but actually you would expect one, but you see these high uncertainties. Okay, let's assume just that beyond 40 degrees, we don't have a further increase. It's just that our density levels off and remains more or less the same intensity as for a slope of 40 degrees. So I'm doing that here. I'm just saying, okay, there's a maximum slope of 40, and everything that's exceeding a slope of 40 degrees is getting the value 40. This is, for these kinds of models, often quite helpful also, because since they are exponential, you might easily then, for very high slope values, where perhaps by chance or for whatever reason, never a landslide occurred, you might get a super high density, estimated density of landslides. So let's comment out this one. Okay. So this is then, now our data goes only to 40 degrees, and that would be just the dependence on that, on landslide density on slope. These indicators down here represent the individual landslides and their elevation, and their slope values. Okay, let's also create some data with or some covariates that include the geology. Now, we had a geological map which is very detailed. It's not a very high map scale, but contained a lot of information about the different lithologies. And here it was necessary to amalgamate those different lithologies, because you won't be able to fit a model with, let's say, 40 different values of a nominal variable. So this is shown just here, I think. So for, well, limestone, shale, and so forth, we put into different lithozones. These were put into lithozone 1. lithozone 2. There are a couple of different lithologies till 5, where which represent the most or the strongest, or what we thought were amongst the strongest lithologies. So in the end, we have 5 different lithologies, for each of which we try to find out, well, what is its influence on the occurrence of landslides. Okay, so in that piece of code, we're just reading that data, and then we can also visualize it. So we see we have 5 different values, nominal values, that change along the road. So this is, again, an elevation profile of the road, and then we also see the different classes of the lithologies. Okay, so now we have a couple of potential predictor variables. Some of them are metric, like slope. One, like rainfall, is also metric. And then there are some nominal variables, for example, like road widening. Okay, the only thing that we haven't solved so far is, well, how do we deal with these different products, with these different rainfall products, if we want to have those as a potential predictor variable. Okay, they all show different patterns, and, well, one way would also be here, well, to run the model in a way that we test which of these rainfall products works well or increases the predictive capability of the model. So what are we doing here? Now this is a bit of a longer code, but what I actually do is I use fit-log linear, the parametric modeling approach that I showcased before. And this parametric model includes one of the different rainfall products, as well as the smooth slope, geology, and road widening. Of course, we also have to say, okay, there are some categorical variables, so the rest is actually only plotting. So I'm going to run this. It will save a couple of images, which we will just look at in detail. So 5 different rainfall products, and they should all be here. Okay, so let's look at what this figure means. So we have done that kind of figure for each rainfall product. So what we see is the individual effects of every predictor variable on landslide density. And what we can see in that case, when we use, in this case it's MSVEP, WEP, as a rainfall product, we can see, and let's start down here. Well, that road widening obviously has an effect. So road widening 1, yes, there was conducted road widening, and yes, in our model, that one would be classified as having an individual effect. So accounting for all other variables and their effects, but this effect alone would then have a nearly doubling of the intensity of landslides. We can also see the effect of lithozones. Okay, so the first 3 lithozones seem to be relatively susceptible to landsliding, whereas the other 2, 4, and 5 are not susceptible. Gradient. Well, we have looked at this one in detail before. Also here we have that strong increase with up to 40 degrees, okay? And then what about the MSWEP? With increasing accumulated rainfall, we would have a decreasing landslide intensity. Doesn't really make sense. We also see we have a lot of uncertainty about this estimate. Actually, it doesn't play actually a role. You could also fit or draw a line which is basically horizontal. That is not a statistical no predictor that would help us in any way. IMERC, another rainfall product, it's the same, no influence. For IMD2, no influence. IMD1, yes, there is an influence, but also again a negative one. That's weird. The only one that actually produces a effect that we think makes sense is the CHIRPS version 2 rainfall product, which shows this increase, or that shows that with an increase in accumulated rainfall, you would also have an increase in landslide density. Now we are here at a point where we then have to ask ourselves, well, what are we actually going to do? Are we now verifying the rainfall product, or are we actually trying to model our landslides? In that case, we are getting in a kind of vicious circle of where we justify to use one product just because it's working better to predict our landslide data. So in terms of the review process that we had, that was one of the things that was also notified by the reviewers, and I fully agree. Yes, that's a problem, but what could you do better than just going for one of the products that increases your or increase your model? So the only thing that we could safely say is that independent of what kind of what rainfall data we take, the patterns that we can observe for the influence of the other variables is not affected by those products that much. So whatever rainfall product we use, it's not always the same, like the effect of the different other variables changes, but not tremendously, okay? So we said, okay, we can increase our model or the predictive ability of our model by using chirps, but this choice might be a bit deliberate. It's just justified by saying, okay, it improves our model, but it actually doesn't affect how the other variables are judged. Okay, but that's perhaps also something that we can discuss in a second. Okay, but based on that, well, now deciding that we would use chirps, we can fit our model. And that's basically just these few lines. We use fit log linear, or point pattern P, and these different predictor variables, chirps, smooth slope, geology, road widening. And we say, okay, geology and road widening are categorical variables. Okay, that's super fast. Model is fitted. So what is actually running in behind? That's a generalized linear model. And yeah, so a logistic regression, how that is solved. And yeah, so that's evaluated super quickly. Now the last lines here, not the entire last, but here a big chunk of code now visualizes the model. So you see, usually the model itself is just a few lines of code. It's just everything around it, like the plotting and all of it, that makes these codes so massive. Okay, so that was also the figure that Jürgen showed to you. And it shows, again, the elevation profile with these different dots showing the landslides. This is a smoothed version of the landslide density, showing the overall pattern. We see the accumulated rainfall as shown or as modeled by chirps. We see the mean upslope gradient. These envelopes are just for visualization purposes, are not actually required. The lithozones, with these 5 different lithozones that we included, and whether a section of that is actually experienced road widening or not. I usually like to create figures so that I just have to run the code and everything is done. But in that case, I don't know why I didn't do that. But it doesn't work. I would do this, of course, for final publication to align all these panels so that they appear nicely in the figure. Okay, now finally, model performance. How well does the model now work? Actually, we can see, okay, the patterns, they agree quite well, and that's often also an important thing to do, to visualize the results and to visually interpret them. But there are two things also that we can use to quantify how good a model works. And one, for example, is the so-called ROC curve, the receiver operating characteristics curve, which shows basically the false positive rate versus true positive rate. So how good are we in identifying landslides and to not identify not where no landslides are. So I'm going to run that code. There are two panels which I slide or briefly describe. So first of all, this is the ROC curve. So if a process is completely random and we cannot predict it, so that means that a random predictor would be as good as our model, then this line here would follow the main diagonal. And that would also mean that the AUC value is the area under the curve, under the ROC curve, would be 0.5. So 0.5 is the worst thing you can get, basically. Alternatively, at best you would have perhaps a ROC curve that goes up here and then like this. Then you would have a 1. So ROC or AUC value ranges between 0.5 and 1, 1 being just a perfect classifier, and 0.5 just a random classifier. We are somewhere, of course, in between, and let's see, I think I probably have calculated also the AUC value. It's something about 0.77 with some uncertainties going up to 0.8. So it's fairly okay. So a lot of susceptibility studies attain values like this. Okay, so we're not in absolutely bad range. But of course, since the density is still relatively low, it's difficult to pinpoint the exact locations of landslides. But what we, I think, gain correctly is the spatial pattern of landslides. So the actual pattern of landslides is, so the density, like a smoothed estimate of the density, is shown by that black curve. And our model, different realizations of that model, and we calculate also the densities, are shown as these gray curves. So just we simulate landslides, smooth it, and so on. And that would basically agree very well with these observed densities, which makes us believe that, it's working not so bad, actually, to predict the locations. And now going back to that figure here, not only predict the locations, but also to have an idea about the controls that affect their locations. So with that, I'm more or less done. Do you have questions? I also showed that there is some critical issues in that analysis, and I'm happy to discuss these. Like for example, one, the problem with the accumulated rainfall product. I don't know, perhaps you have other ideas of how to solve that, or other approaches that we could take. Or are there any other questions? Just go ahead. It's taken along the line, so we have a grid, and we are extracting for each point along the road the grid value. So that's the paper that belongs to this one. And here, here it's a different case. So what we're looking here at is a DEM, a river network, and the location of beaver dams. Okay, so where are beavers? And the idea was, we can actually create a very simple model. Well, I'm not a biologist, and biologists will probably criticize that very quickly, but I would say, okay, beavers are there where enough water is, but probably not too much, I don't know. And gradient is not too steep, because if gradient is too steep, their nests will be destroyed during the next flood. So we tested just a simple model of gradient and area, upstream area being a proxy for discharge. And well, when we do that for this point pattern, this also shows up, okay? So we have a decline in beaver dams with increasing river gradient. And we have such a hump-shaped curve concerning the area. So in the really big rivers, they were at least, or not recorded, well, we didn't record that data by ourselves, but just had it for that area or for that basin. So there was with a maximum at 10 to the 7 square meters catchments that hosted beavers. Now we can use that model to predict beaver locations, but then we see, okay, it doesn't match very well perhaps with the observed locations. Rather, these locations seem to cluster, which makes sense. I mean, perhaps beavers will have their offsprings next to them, whatever. I don't know. Perhaps it's also inherent in the data. One can test this then using the K function calculated on a network. So the K function tells me what is the mean number of, or what is the intensity of points around a particular point or some representative point as a function of radius. If you have a two-dimensional point pattern, it's pretty clear that the larger the radius becomes, the intensity grows with, where's my chalk? Not here. So the intensity then grows with the r square times pi, because you just increase the area. Sorry, no, that should be n. And so you divide that by the intensity of the point pattern, and this gives you the K function, so more or less. On the network, that's a bit different. It can be a straight line, but it depends a bit on network topology. So, but if there was no second order effect, then you would expect this red line to run within these, let's say, confidence bounds or acceptance intervals of this null model where there is no point interaction, no clustering, nothing. But we can see that our red line runs far above that line, suggesting what we can actually also see visually, that there's a lot of clustering in that data. Okay, so there, for the beaver locations, we can expect a second order effect. And that is something that we are currently also working on, how to include that even better in the model. So far, we can only do this in an exploratory way, using, for example, the K function. For modeling these types of processes, let's say that's an active field of research so far. And since I'm not a statistician, it's rather something where I have to rely on what's going to happen in the next years in that domain. Okay, if that's not the case, then perhaps just a few concluding words. Well, I hope that, also speaking for Jürgen, who's busy here helping out, which is good, I hope that you could take something along from that short course. And it's, let's say, not something that you would probably apply on a regular basis, but perhaps for some of the phenomenon that your research deals with, perhaps it's something that you can apply. And I hope that we provided something useful to you. So this PPS can be used to analyze, model, and simulate and visualize point patterns on stream networks or other networks. So, for example, species sightings, waterfalls, riffle pool sequences. Riffle pool sequences are something where you have also a lot of interactions because they have a characteristic spacing, for example. Beaver dams, bed load tracers, whatsoever. So, and what is new about it is that PPS attempts to combine digital terrain analysis, as you know it in GIS and Topotoolbox, with a field of spatial statistics called point pattern analysis. And as we have done it here, you can use it for other networks and not only stream networks. That should be, however, dendritical networks. That's kind of a drawback that we currently just can do that. Going beyond that would also mean that we had to rewrite a lot of algorithms. So it's likely not going to happen. It's more likely being applied to dendritical networks so far. But by that, thanks for listening and